Okay guys, there's going to be a smorgasbord of different integrals in this lesson, and they're all going to be trig integrals, and we're going to just take a look at a lot of different techniques that get used, just so you've seen these, and they're not a big shock to you when they first come up, whether it's in an application that we do or in college. So let's start with tangent squared. This one's probably come up in the past, and the trick here is we want to use one of our identities from pre-cal. The identity we want is tan squared plus 1 equals secant squared, so that means that tan squared is 1 minus, or I'm sorry, secant squared x minus 1. And the reason we want to do that is because those are functions that are on my list, whereas tan squared is not on my list. Okay, so there we go. And then that one easily comes down to being tangent x minus x plus c. We've seen cosine squared and sine squared come up before, so let's just reiterate that we're going to use the half angle identity, which is 1/2 1 plus cosine 2x for that one. And then over here you'll use almost the same thing, but it's 1/2 1 minus cosine 2x. And then you split that up, you make a u sub on the cosine 2x part, and you're off to the races. I'm not going to spend time doing that here. You've seen those. We've also seen tangent come up before. We know that we're going to convert that to sine x over cosine x, and we're going to make the u substitution. So I can change it into a 1 over u du, and I end up with the negative natural log of cosine x. Or, if you'd rather put the negative 1 in the exponent of cosine, you would have the natural log of secant x plus c. This one came up in the worksheet on Thursday, and just good to know for future reference. You can integrate secant x. You need a neat trick, and the trick is to multiply by 1. And the one you're going to multiply by is secant x plus tangent x over secant x plus tangent x. And no, you would not just think to do that. It just comes from trial and error and from playing around with patterns here and knowing what you're trying to create. Okay, when you distribute the numerator out, you get secant squared x plus secant x tan x, and that's nice because those are the two derivatives of the denominator, which allows me to use the natural log pattern on this. So this means now you can do all of the trig functions, antiderivatives, and you can also do all of the trig functions squared, antiderivatives. Okay, now let's take a look at using some other identities to make some of these integrals a little bit nicer. So let's start with some cubes. We've got tan cubed, we've got cosine cubed, and we've got secant cubed. Now I believe secant cubed came up in class, so I may not do that one here. Okay, but this is in class, it's done with parts, and you're also looking for the song that never ends, or at least you're hoping it never ends. Okay, so I'll just write song that never ends. You can refer back to your notes from class if you finished that one, and if you didn't finish that one, well, I don't want to ruin the fun, so I'll just leave that one out here. Now, what are we going to do with tangent cubed? Well, let's see here. If we break this up into tan x times tan squared x, I might be able to use an identity to my advantage here. Let's replace tangent squared x with the identity 1 minus, I'm sorry, I did it again. It's secant squared x minus 1. My fault. Okay, now why is that nice? Okay, if we distribute and make this two integrals, we're going to get tangent x times its derivative, secant squared x, that's good, and a second integral, subtracted integral of tangent, and we know that one. So this one, the first one, is going to be a u sub, that's going to be u, and the du is already built in there, so we know we're going to have 1/2 your u, which is tan squared, right? U squared plus a c, and then over here we already know that that's going to be minus and minus becomes a plus, the natural log of cosine x. Okay, so you can see we use multiple techniques. Identities are very helpful for the trig guys. What about cosine cubed? Well, let's try the same thing here. Let's take cosine cubed and break it up into cosine x and cosine squared x. And then let's use an identity, Pythagorean identity here. And let's make this 1 minus sine squared x dx. And once again, let's split this up. Cosine x is a nice integral. I would love to have that one every day. And subtract this integral. And let's just rearrange it. Sine squared x cosine x dx. If I make u sine x, I'm in business because the du is already in this problem. Okay, so I would have u squared du. So I'm going to have minus 1/3 sine cubed x plus a constant. And this one's all ready to go, just sine x. Okay, so very nice. Play around with this one. If you're not already done, then you'll be able to do the integrals of all the trig functions cubed. Some of those rules also apply to fourth powers and higher. One of them does not. I want to take a look at that real quick. Let's say you had cosine to the fourth x dx. And if we try to split that up, it's not going to be very nice. And the trick to this one is to split it up this way. Cosine squared x times cosine squared x. And then we need to use the half angle identities on each of those. So let's review. That's 1/2 1 plus cosine 2x. Okay, you've got two of those being multiplied. And yes, we're going to expand all this. Let's take the 1/4 out, and we're going to have 1 plus 2 cosine 2x plus cosine squared 2x. And what are we going to do next? You're going to split this up. This one's good, and this one we're going to use, guess again, the half angle identity. Okay, so let me just write this up real quick. You're going to have 1/4 1 dx plus 1/4 integral 2 cosine 2x dx. That's good. It's going to be a u sub, possibly a mental u sub, plus 1/4. And now I need the half angle identity for this, which is going to be 1/2 1 plus cosine, not 2x this time, but 4x. Throw a dx in the back of that and you're ready to go. And let's just take a look at one more. You had a chance to mess with this a little bit in class. And I don't want to do this one. I want to change it around. Let's do the square root of 1 minus x squared dx. Now you got a chance to do this with a definite integral, but I like the beauty of this with the indefinite integral, and you see some nice things happen here. So when you have quadratics, either inside a square root or not, trig subs end up being very helpful because of the Pythagorean identities. Now we should know that there's a couple that have 1 minus involved with them. Okay, 1 minus sine squared x is equal to cosine squared x. 1 minus cosine squared x is equal to sine squared x. There's others. Some of these can be done multiple ways. But I see a 1 minus something squared. I'm thinking trig. So let's let x equal, let's use sine x. Okay, and let's do some substitution here. You're going to have the square root of 1 minus sine squared x. And now we got to replace the dx. Okay, so what we know dx d theta. And I'm sorry, I should have replaced this correctly. I can't use x twice, I need a different variable. So let's use theta. So let x equal sine theta. There we go. Dx d theta equals cosine theta. Okay, and that means our dx gets replaced with cosine theta d theta. Okay. Now, 1 minus sine squared is cosine squared theta. We have a cosine theta on the outside and a d theta. Now, our assumption here, okay, is that theta will be less than pi over 2 and more than 0 for our examples here. I know that's a little iffy, but here's the deal. I need to use the square root and the square as inverse operations. Normally that's absolute value, but if we know cosine's positive, I can just drop the bars. And so for this context, we're going to drop the absolute value bars and say that the square root of a square is what's inside. And so I'll have cosine theta times cosine theta. Which means I need the half angle identity. 1/2, 1 plus cosine 2 theta d theta. Now, antiderivative. I'm not going to convert back just yet. Okay, 1/2 theta plus 1/4 sine 2 theta plus a constant. And now we gotta convert back to x's. And here's where the fun begins. Okay, we go back up here and look at our substitution. I need to replace a theta. So theta is going to be the arc sine of x. And now I have to replace a sine 2 theta. I think now I need a diagram. So we draw a little diagram here that represents x equals the sine of theta. So here's theta. Ratio of opposite to hypotenuse has to be x, which is x over 1. And that means that the third side, to be in proportion, needs to look like this. Now, sine of 2 theta. Well, 2 theta is not in this diagram, so I need the identity for sine 2 theta, which is 2 sine theta cosine theta. And now I can replace. Okay, so 2, the sine of theta in this diagram, we already know is x over 1, and the cosine of theta is the square root of 1 minus x squared. And you can check it if you don't believe me, but if you take the derivative of this answer, you should get square root of 1 plus x squared when you're done.